The double bond in an alkene is greatly responsible for the physical and chemical properties of these compounds. The double bond acts as source of electrons, and hence alkenes react with electron deficient species. These species are known as electrophiles and may lead to an electrophilic addition. In the presence of metal catalysts such as platinum, palladium, or nickel, hydrogen is added to the double bond of an alkene to form an alkane. The addition of hydrogen is called hydrogenation. Because hydrogenation reactions require a catalyst, they are catalytic hydrogenations. Alkenes are easily converted by halogens to alkyl halides, where two halogen atoms are added to two carbon at neighboring positions. The reaction is relatively easy carried out at room temperature and does not require light. Two reactants are mixed in an inert solvent such as dichloromethane or carbon tetrachloride. This reaction is called halogenation in inert solvent. Addition of bromine in inert solvent is an extremely useful tool employed to detect the presence of double bond in an unknown organic compound. Bromine solution in dichloromethane is reddish brown color. Addition of an unsaturated molecule rapidly decolorizes the reddish brown color of bromine. This is an unsaturation test called as bromine test to confirm the presence of a carbon-carbon double bond. If water rather than inert solvent is used as a solvent, the product of the reaction will be a vicinal halohydrine. A vicinal halohydrine is an organic molecule that contains both a halogen and a hydroxyl group bonded to neighboring carbons. This halogenation in water reaction follows the general rule for electrophilic addition reaction, which is the Markovnikov rule. Markovnikov rule states that in addition reaction, the electrophile is added to the sp2 carbon that is bonded to the greater number of hydrogens. In halogenation in water reaction, the Br plus or Cl plus is added to carbon that bonded to greater number of hydrogen, and the OH minus is added to the neighboring carbon. This reaction also can be used as unsaturation test. In the reaction between an alkene and hydrogen halide, HX, where X is fluorine, chlorine, bromine, or iodine, the hydrogen halide adds across the double bond, thereby producing the corresponding alkyl halide. This hydrohalogenation reaction will also follow the Markovnikov rule, where the electrophile, which is the H+, will be added to the sp2 carbon that contain greater number of hydrogen, while the X- will be added to the neighboring carbon. For the reaction of alkene in the hydrogen bromide in the presence of peroxide, it will follow an anti-Markovnikov rule, where the electrophile H+ is added to the sp2 carbon that has a smaller number of hydrogen, while the Br- is added to the sp2 carbon that has greater number of hydrogen. The reaction of an alkene with acidified water will produce an alcohol. This reaction is called hydration. In this reaction, Markovnikov rule is applied to determine the product, where the electrophile, the H+, will be added to the sp2 carbon that contain greater number of hydrogen, while the OH- will be added to the neighboring carbon. When an alkene is treated with ozone, the double bond breaks and the carbon that were doubly bonded to each other are now doubly bonded to oxygen instead. The oxygen reaction is known as ozonolysis. The reaction of an alkene with hot acidified potassium permanganate will also undergo an oxidative cleavage. This reaction will produce ketones or carboxylic acid depending on how many hydrogen atom is bonded to the sp2 carbon. If there is no hydrogen atom bonded to the sp2 carbon, the product will be a ketone. But if there is one hydrogen atom on the sp2 carbon, the product will be a carboxylic acid. Terminal alkenes with two hydrogen atoms on sp2 carbon form carbon dioxide as a product and water as a byproduct. The oxidation of alkenes using ozonolysis or hot acidified K-aminophos solution are often used to identify the position of double bond in alkene. By identifying the products, the position of the double bond in the alkene can be determined. For example, if ozonolysis of an alkene produces butanol and pentanol, the location of carbon-carbon double bond is found by removing the oxygen atoms from the carbonic compounds and joining the carbon atoms with a double bond. This gives 3-methyl-3-octene. If the reaction of an alkene with hot acidified KMnO4 produces a propanoic acid and 2-hexanon, the location of carbon-carbon double bond is found by removing the oxygen atoms from the carboxyl and carbonic compound and joining the carbon atoms with a double bond. This gives 4-methyl-3-octene.